All right, units. So units are very important because they come with measurements, and measurements have significant figures. So if somebody says, get to the airport in 3, what does that really mean? Does it mean it takes you 3 hours because you're far away or maybe you're stuck in traffic? Does it mean 3 minutes because you're ready to walk in, the loading gate? Is it because it takes 3 gallons of fuel because you have a big truck? Who knows? The problem with units is there's so many different units and they come from so many different organizations, whether it's the old English system or the metric system or the new international system. What scientists typically use is the SI system. This is our standard set of units, and this is what most nations use in their scientific research. So a lot of people use kilograms, they use meters, both of which are in the metric system. We use moles in chemistry for the amount of substance. We use Kelvin in temperature, which is not really English or metric. And the only one that's really universal is time, and that's in seconds. So as we look at the base SI units, we're dealing with meters, and meters are big. So oftentimes in intro chem, we're going to be dealing with centimeters, which is easily converted to meters. Oftentimes we use mass in kilograms, but again, that's way too big for chemistry, so typically we'll use grams on our balance in class. Time does go in seconds, so that's easy. There's no conversion there, other than for minutes and hours. But unfortunately, temperature is in Kelvin, and that'll be a conversion from either Celsius or Fahrenheit or both. And then over the next 3 weeks, we're going to spend a tremendous amount of time dealing with moles and mole conversions. One of the biggest problems with numbers and measurements is where did they come from? If we have an English unit of yard and a metric unit of meters, somebody has to measure the difference. And as soon as somebody measures that difference, they introduce uncertainty. And if uncertainty is introduced, then we have to worry about significant figures, and then calculations deal with significant figures like we just showed in other videos. Only one conversion is really exact, and that's 1 inch is 2.54 centimeters. That's the only one between the English system and the metric system that we use in intro chem that doesn't require significant figure rules when you multiply or divide or add or subtract, that kind of thing. As we look at mass, we have to realize that mass is different than weight. Weight is based on gravity. In chemistry, we deal with mass because mass is unchanged from this planet to the next. So the amount of matter that you contain is not going to change when you go to the moon. The ability of that planet to pull you down to its surface does, and that's where you can weigh a whole lot less on the moon, but still have the same amount of mass. The standard unit we mentioned is a kilogram, but chemistry uses a gram because it's much smaller and more meaningful to our small amounts of mass that we use. To be able to get from our system to the chemistry kind of system, we need to use 454 grams equals 1 pound. You'll be given that on the exam. As we look at volume, volume is typically used in liters. We typically use milliliters because we don't want to have a lot of waste. It's probably very important for the nurses to know that chemistry uses the milliliter, which is the same as a cubic centimeter or a cc, same thing that's in a syringe. So if there's 1,000 milliliters in a liter, then there's 1,000 cubic centimeters in 1 liter. To get from our system to theirs, we're going to use 946 milliliters is equal to 1 quart. And that'll help us get from, say, liters to gallons eventually. One of the major hurdles of this chapter is to learn the metric system. If you're from a different country, then that's not a big problem because that's probably the system that you grew up on. But the United States is still holding out. I think in the 1970s, they said we would change from the metric system, but we never did. So looking at the metric system, we have lots of different prefixes, all of which are just powers of 10 different. So the one thing good about the metric system is it's very easy to use once you learn it because it's all powers of 10. There is no random 12 inches in a foot, 1 foot, or 3 feet in a yard, that kind of thing. It's all perfectly powers of 10 based and not completely random as the English system tends to be. And one thing also nice about it is the meter, liter, gram, calories, bytes, hertz, all of those units still use the metric system, even though they're in mass and volume and storage, calories and energy, and even time. All of these can be transposed just by powers of 10, which is nice. So looking at powers 10s, we start from a trillion and we go to a trillionth. So in this upper category, there's all, it's 1,000 per prefix. So we go from a trillion tera to a billion giga to a million mega. Probably hear the lottery of mega millions. That's where they get it from. Kilo is 1,000. We jump over the other two units that are not mentioned in this textbook, so I won't even mention their names. We jump down to the standard unit, which is the meter, liter, gram in green. And then we go smaller. So in these first three, they're by 1/10th place, not 3 like above. So we have deci, centi, milli. So 10th, 100th, and 1,000th. And then after that, we're going, again, 3 powers of 10 every jump. So micro being the size of microbiology or viruses. Jump another 3, go to nano, getting close to the size of an atom, and those wavelengths we saw early in the semester, and then eventually pico, which is a trillionth. So here's a very disturbing mnemonic to help you memorize it. Terry for Tara. Got mad, kicked my dog, chased Millie's mule, notified the police. So it does have a little bit of animal brutality, but we did notify the police because we don't want that. But usually the weirder the sentence, the easier it is to remember these obscure lists of prefixes like we see in organic chemistry or inorganic chemistry before it. So Terry for Tara, giga for got, mad for mega, all capital letters, all very large units. Kilo for kicked, my would be the meter standard unit, which is interchangeable with lots of other units. Deci with dog, centi with chased, milli with milli. Mule as mu, the Greek letter, kind of weird, but looks like a U with a long tail on the other side. And then nano for notify and pico for police. So if you remember those letters, we can use those to do conversions. And what's nice about Intro Chem in my class is I give you a metric ruler that shows you the powers of 10. You just have to memorize the letters in order. If you memorize the letters in order, you can use rulers to show the distance needed to travel from one unit to another without a calculator. So as we look at these examples and these rulers, there's some practice in the experiments in the lab book over this as well. And we'll hand this out in class, or at least something similar to it. So if we have 24 trillion meters, notice the unit that we have here is meters. So when we find the standard unit, which is here, there's where meter would sit. And notice to the right side edge, we would put the decimal. Even though it's not here, we're pretending by putting it on that right side edge. And then for every number that we have, we just fill in all those spaces all the way down. And when we run out of numbers, then we can interchange any kind of unit we want. Let's say we wanted to go to kilo. We would just take the decimal from here and move it to the right side edge of kilo, and we're done. Maybe instead we wanted mega. We could go all the way down there and at the decimal instead. In our case, we wanted to go all the way down to giga, and the only numbers left were the 2 and the 4. The answer would be 24, and you can convert that to scientific notation. So notice the beauty of the metric table is you can change it from any direction you want. If we wanted to keep going further, you could imagine that if we wanted to go to a small unit, you could just keep adding zeros and get a unit of micro by moving the decimal over to the opposite direction. So what's nice about the metric ruler is if you memorize the letters, you can plug the number into the scale and size it big or small as needed very, very quickly. So there the answer was 24. If we notice on this next one, We have meters again, so right side edge of meters again. We're going to move it to the kilo. So as we move it to kilo, our answer goes from 4,000 to 4. And then we can put that into scientific notation for practice. Down here we have a small number, so notice we have meters again. This time we have a small number, so we went and wrote it left of that decimal point. And then as we moved from meter to millimeter, the answer became 25. So it's very important in both of these situations to realize that if you know the list of letters, you're in pretty good shape. We'll also see pressure, not this chapter, but eventually. We'll see it in week 16 when we cover gases and moles, specifically with gases. So we'll worry about that at a later time. There is a pretty big focus for temperature in this chapter. Temperature, there's 3 scales, and chemistry uses Kelvin, which is an absolute scale that has no negative numbers. So let's show you a little bit about those. The first temperature scale was created by Daniel Fahrenheit. He used salted ice to make 0, which happens to be way down here, unfortunately. And because he used salted ice, which is the same temperature to make frozen ice cream, if you ever made homemade ice cream, you've probably seen that, it ended up being 32 as the freezing point for water, which is pretty random, I'll be honest. He also set his 100 degrees to be the temperature of his armpit, because he thought those 2 temperatures would be easy to kind of reproduce around the world from his thermometers. Long story short, though, water boils at 212, it freezes at 32, and that's 180 degrees difference, which is giving us a lot of numbers to use, which makes it very accurate. And that's why we still use Fahrenheit. It's much more accurate than Celsius that the rest of the world uses, because we have 180 markings on our thermometers to span that difference, and everybody else only has 100. So it's almost twice as accurate. But it is more obscure. So Anders Celsius, several years later, said, let's just fix it by making it 0 and 100, which is easier to remember. And that's probably why. William Thomson said that that was messing up his physics calculations. He needed no negative numbers, so he offset this temperature by 273 so that he could have the coldest possible temperature be 0. So really, Kelvin and Celsius are the same exact temperature scale, just offset to avoid negative numbers. So pay attention to the coldest possible temperatures. That's a question in the homework. But most importantly, pay attention that Kelvin and Celsius are the same, just offset by 273 degrees. We also want to realize that temperature is a great way to segue into unit conversions. If we have a temperature like Fahrenheit, notice we're going to have to adjust the temperature because 0 and 32 are not the same. So if we have some number in Fahrenheit, we can subtract 32 first to offset that scale. And then what we'll need to do is get rid of Fahrenheit. And this is an important process for the rest of the semester. We have to make sure that these units cancel. And the easiest way to do that is to put them in the numerator and the denominator. We also get degrees Celsius on top. We just need a way to relate Celsius and Fahrenheit. And that's what we have. We have where water boils and where water freezes for all 3 thermometers. And this tells us that if we have 100 degrees here, it compares to 180 degrees there. So for every 180, Celsius only travels 100. And now we can convert to Celsius. However, if we have Celsius, we would have to get rid of Celsius first by putting it on the bottom. Those units would cancel. For every 100 Celsius, there's 180 Fahrenheit. And then we could add our 32 to correct for it. But notice we had to get to Fahrenheit first before we could add 32 Fahrenheit to it. There would be no adding Fahrenheit to Celsius that would make sense. And then if we have some kind of Celsius temperature, we could add 273 to get to Kelvin. And those are our temperature conversions. There are two shortcuts, and that's that if you know that 180 versus 100 is the conversion from Fahrenheit to Celsius and vice versa, you can just reduce that to 9/5. So using this is a little bit faster. Units are already, canceled in these kinds of setups. Just remember to use parentheses where needed, otherwise PEMDAS will not be followed. So before we jump ship on to density, let's do a practice problem. So let's pretend that, we go across the border to Canada or Mexico, and we're taking our temperature to make sure we're not sick. So if 98.6 is 98.6 Fahrenheit is normal, what would be normal in Celsius? Well, based on what we just saw, we would have to subtract 32 degrees first. Once we subtract 32, we need to make sure that Fahrenheit cancels. So this is what tells us that Fahrenheit should go on the bottom, because then it can cancel top to bottom. And then we can put Celsius up top. The difference between freezing and melting of water would be 180 in Fahrenheit versus 100 in Celsius. And when you throw this in your calculator, you're going to get 37. Problem is, we started with 3 significant figures. So what's missing would be 0.0 to keep 3 significant figures. Based on 37, we could say 37 plus 273 to convert it to Kelvin, and that will give us 310. The problem with 310 is if we still have 3 significant figures, 310 only has 2. So either we underline and put Kelvin, or we have 310 with a decimal after it to show that that 0 matters, Kelvin. That would work too. Let's prove we can go backwards. If we have 37 degrees Celsius, we need to get rid of Celsius, go to Fahrenheit. Notice units cancel like they should, top to bottom. That's going to be super repetitive over the next 3 weeks. We have 180 Fahrenheit per 100 degrees Celsius for the melting points to boiling points of water. Once we're in Fahrenheit, then we can add 32 to adjust for the scale of where they start, and then we'll get our 98.6 back. So pay attention to sig figs, pay attention to temperature conversions. Temperature conversions are about 10 of our questions on exam 5 at the end of the semester. You will not be given temperature conversion charts. You'll have to remember that and be able to use them. We'll come back in a separate video to do more conversions, this time with density.